Now, you and I, we use base 10. That's what we use. So when you write a number, 294, that's actually base 10. The weight of this location, the weight of that, it's 10 to the 0, which is what? 1. The weight of this location is what? 10 to the first, which is 10. The weight of this location is what? 10 to the second, which is what? 100. That's why we call them the ones, the tens, the hundreds, and the next one is what? 10,000 or 1,000, then 10,000, 100,000, so forth. 10 to the third, 10 to the fourth, 10 to the fifth, and so forth. So when you see a number like this, the value of that number, it's really 2 times the weight, and the weight of that digit is 100, plus, this is the tens, 9 times the weight of that, which is 10, plus 4 times the weight of that, which is 1. So that number is what? 200, bless you, plus 90, plus 4, and that's where the 294 came from. And if that number has decimal, let's say it was 15.214. The weight of this one is what? 10 to what power? How about negative 3? So that's 1 over 1,000. Number 3 digits to the right. The weight of this is 10 to the negative 2, which is 1 over 100. The weight of this, 10 to the minus 1, which is 1/10. The weight of this, that's 10 to the 0, which is 1. And the weight of this, 10 to the 1, which is 10. So that number is equivalent to what? 1 times 10 plus 5 times 1, the weight of that is 1, plus 2 times 1/10, plus 1 times what? 100, plus 4 times 1,000. One times 10 is 10, plus 5, plus 2 over 10, plus 1 over 100, plus 4 over 1,000. If you want to take your calculator and divide these numbers and add them, it should give me the same number, 15.214. This is a Casio. I'm not really good with the Casio, but what I like about it is the resolution is phenomenal. Just got to make sure I go back to the main. See. 10. Trying to keep away from. Plus 5, plus 2 divided by 10, plus 1 divided by 100, plus 4 divided by 1,000, not 100 here, the last one, right? Plus 4 divided by 1,000, 15.214, what we started with. Now, unfortunately, the computer doesn't speak this language. You and I speak base 10, number system, that's base 10. So this one is base 10. Then what does the computer speak then? You know the computer speak what? Binary language. That's base what? 2. Before I leave that, base 10, what is the largest one single digit? So when you base 10, what's the smallest number we use? 0. What's the largest digit? 9. 0 to 9. It's always 1 less than the base. Well, if the machine, actually the computer uses binary, that's base 2. That means the smallest digit is going to be what? 0. And the largest digit is going to be 1 less than the base, which is what? 1. And there are no other options. So 0 and 1. Everything has to be 0 and 1. So when you go to write that 294, or when you write a number like this, 1, 0, 1, 1, 0, 1, we're saying, oh, what is that equal to? The machine prints that, but to me it means gibberish. What is that number equivalent to? Well, let's do the same thing we did with base 10. What's the weight of this digit? That's 2 to the 0, which is what? 1. This one, 2 to the 1, which is what? 2. This is 2 to what? Second, which is what? 4. Next one, 2 to the third, which is what? 8. Let me stop here for a second. A lot of people call this one 8421 base. 8421. 8421. That's where it came from, the name. If you're using 4 digits. In our book, you'll see in a minute, we'll be dealing with 4 digits, and they call this, instead of binary, 8421. But that's what it means. But now if you have another digit 5, this becomes what? That's 2 to the 4th, which is what? 16. And the last one, 2 to the 5th, which is 32. So the value of that number in you and I, on our language, that's 1 times 32 plus 0 times 16 plus 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1 times 1. 1 times 32 is what? 32. This is 0. This is 8, 4, 0, 1. Is that 45? That's a 45. So to you and I, that number represent, so when I write that number on the test, on the first test, you'll see I'm going to give you numbers like this. I go, that's base 2. Tell me, what is that as a base 10? What is that equal to? I need to know what that is. And the answer to that is what?
45.
That's a 45. So that's how we convert from base binary to base 10.
How do we go from base 10 to binary?
Coming up in a few minutes, Stephen. But I'm glad you're excited about it. That's good. Yep. What about if I have decimal numbers first before I get you to that one? 101.11. Again, just like the other ones. This is base 2. And I want to know what is that in base 10. Boy, I didn't even bring an eraser today. I better not make a mistake. One 101.11. Again, the weight of this. This is 2 to what power?
Negative 2.
-2, which is a 4th. This one, 2 to the -1, a half. 2 to the 0, 1. 2 to the 1, 2. 2 to the second, there's my mistake, that's a 4. So this number will be 1 times 4, 0 times 2, plus 1 times 1, plus 1 times a half, plus 1 times a 4th. One times 4 is what? 4. 0 times anything is 0. 1 times 1 is 1. 1 times a half is a half. 1 times a 4th is a 4th. That's 5 plus. Now, if you want to add these numbers, 1/2 and 1/4, what do you need? LCD, right? Which is that a 4, right? That's 2/4 plus 1/4. That's 3/4. which is decimal number what? 5.375?
Yep.
So in decimal, that's 5.75. Now, Stephen said, well, how do you go backward? How do you go from this to that? So when you and I sit on the computer, you start typing stuff. You type in, enter your age, and you put in 21 or 23, or in my case, 59. You go, uh-oh. Machine needs to convert that because the machine doesn't speak that language. Whatever we give to the machine has to be converted to ones and zeros. So what does the machine has to write for 59? How do we convert 59 to binary ones and zeros? I'm going to look old as I change it to ones and zeros now. But let's say this is 59, base 10, and I want to change it to base 2. What is that? And here's the process. 59 divided by 2. 59 divided by 2 is what? 29 and a half, which means what? It's really 29 plus a remainder of 1 if you do long division. It's a remainder of 1. Then we take the 29 divided by 2. If it was 28, that would be what? 14? That's 14 plus a remainder of 1. (14) divided by 2. 7 plus a remainder of what? 0. There's no remainder. 7 divided by 2. 3 plus a remainder of 1. 3 divided by 2. 1 remainder of 1. And finally, the 1 divided by 2, which is 0 plus a remainder of 1. Once you reach the 0, you stop right there. Now, you and I, when we write a number, we write them left to right, right? So you're going to read this backward if you're going to write them left to right. This number here goes on the left. So the answer is 1, 1, 1, 0, 1, 1. That's what 59 is. 1 plus 2. Let's see if that's true. The weight of this is 1. 1 times 1 is 1. The weight of this is 2. 1 times 2 is 2. The weight of this is 4. 0 times 4 is 0. The weight of this is 8. 1 times 8 is 8. The weight of this is 16. 1 times 16 is 16. And the weight of this is what? 32 times 1 is 32. Does that add up to 59? 32, that's 48. 50, 58, 59. So that's how we convert from base 10 to base 2. We divide them, long division. You're not going to write 59 and 29.5. The 0.5 means you have a remainder of 1. Now, if that number has a decimal value, let's try one with decimal value. Ask you, how old am I? I'm 21.75 years old. I said, oh, very good. You can't wait for 22. Because if you start counting decimal, that means you're really excited to increase your age. Or if you're 20.75, because you can't wait to hit that 21. That means 29 months. 3 more months to be 21. So this is 21.75. Let's change that. Now we get two parts to deal with. We have the one on the left, we get the one on the right. The one on the left, straightforward. 21 divided by 2. It's 10. What's the remainder? 1. 10 divided by 2, 5, remainder of what? 0. 5 divided by 2, 2, remainder of 1. 2 divided by 2, 1, remainder of 0. And finally, the 1 divided by 2, 0, remainder of 1. 1, 0, 1, 0, 1. The good news here, even if you read them wrong, backward, by luck you'll have the right answer. But you read them bottom up. Sometimes you end up lucky. Don't worry about it. It's the same answer. In this case it is. The other one wasn't. Now what about the decimal? Now the decimal portion, to get that, we multiply instead of divide, multiply by 2. What's 2 times 0.75? 1.5, right? Let's put the fraction portion of it and the decimal. So it's 1 plus the 0.5. Two times 0.75 is 1.5. There's the 1, the whole number, and there's the decimal portion. Now take that decimal, 0.5, multiplied by 2. 2 times 0.5, which is what? 1, and what's the decimal portion?
0.
Once this one's 0, you're done. This one, actually, you read it from top to bottom. It has to be top to bottom, this one. So the answer to this, 0.11. Why top to bottom? Because sometimes it doesn't end. It goes on to infinity. Yep, I'm doing a different one. Yep. And the one that gives you more numbers to it, actually. Been like checking its hard drive since 8 o'clock this morning. Sounds like termites next to me. Let's try the 6. 6 divided by 2 is what? 3 plus a remainder of what? 0. 3 divided by 2. 1, remainder of 1. 1 divided by 2. 0, remainder of 1. So we're going to read them again. These we read them bottom up. 1, 1, 0, and there's the point. Point 28, the decimal portion, multiplied by 2. That's what, 0.56? So that's 0 plus 0.56. There is no whole number to it. So let's put a 0 for the whole number. 0.56 times 2. 1.12, right? There's the 1 plus 0.12. 0.12 times 2. So there's no whole portion to it. 0 plus 0.24. 2 times 0.24. 0 plus 0.48. 2 times 0.48. 0 plus 0.96, right? 0.96 times 2. Hey, fall asleep on me here. 0.96 times 2. What'd you get there? 1.92. 1 plus 0.92. 0.92 times 2. $3.84. Oh no. Oh, 0.92. I said 3. 0.92 times 2. Ugh. 2 times 0.92. Start again. 1.84. 1 plus 0.84. Now the 0.84 times 2. 1.68. 0.68, hopefully will repeat or stop in a minute there. Multiply it by 2. 1.36. So you can see why we have to read this top to bottom, because it might not end. So how many of these digits are you going to carry?
8.
Why 8?
So that's a byte.
Okay, byte is, you're right, byte's 8 bits. It really depends on your machine. Is your machine an 8-bit machine or a 16-bit machine or a 32-bit machine? If your machine is 32-bit machine, the calculator will carry, you want to carry 32 bits. If your machine is an 8-bit machine, you go 8 and you stop. So here I give up. I said, okay, I'm not going to spend all my time on that. One, and there's more. Dot. And there's more to come. So that will do. If I said you have an 8-bit machine, that means for the decimal part you can have 8 locations. You don't need the 9th one because it's going to be 8. You're going to put the first 8 bits in it. So that's how we convert from decimal to binary. Now, there are other codes people use, other number system, especially if the government want to make sure, people not copying stuff. They might use like the octal, they might use the hexadecimal.
So does that mean that's an estimated value?
With this one?
0.28?
Yeah, that'll be an estimation. It will not be exact, unless eventually stop, terminated. But I stopped going through it. You're talking about this one, right? Yeah. This one, because I stopped.
After it stopped, because it repeats the 0.96.
Does it repeat?
Yeah, comes back to 0.96.
So the pattern will continue. Yeah, that will go on. Yeah, that'll be for infinity. That'll be an approximation. Yeah.
So you'll never have a 0.28?
You won't have 0.28 on the money. No.
But close enough.
Yep. It'll be like 6.27999999999999. It's okay. That's good.
Close enough.
Now, what about the octal? Octal means base what? 8. That means your largest number is, the smallest number is going to be 0, and the largest number is going to be what? 7. So you can't have a number more than 7. Sometimes I fall asleep when I'm making a quiz or a test. I go, okay, a test. Convert this. I go, this is going to be wrong now. Why is that wrong?
There's a 9.
I put a 9 there. You can't have a digit here bigger than 7. So every once in a while I fall asleep and I go, oh, convert this. And I look at it, wait a minute, never mind. That can't be. Let me get my eraser here. I need to convert that. I change it. Maybe I'll make it 1 now instead of, now it's a valid number. And again, what is the weight of this digit? Now we're talking about base 8. This is 8 to the 0, which is what? 1. This is 8 to the 1, which is what? 8. 8 to the second, which is what? 64. So that's 2 times 64 plus 1 times 8 plus 6 times 1. 128 plus 8 plus 6, is that 142? So this one and base 10, that's equivalent to 142. And if you get decimals again, oh, again I fell asleep. The weight of this is what? 8 to the minus 3, which is 1 over, what's 8 to the third? 512. This is 8 to the minus 2, 1 over 64. 8,
Oh, it was 8 to negative 2, 8 to the negative 1.
8 to the minus 1, which is 1/8. And this is 8 to the 0, which is 1. Seven times 1 plus 2 times 1/8 plus 5 times 164 plus 4 times 1 over 512. 7 times 1 is 7. Is that 2 over 8, which is 1 over 4? Plus 5 over 64 plus 4 over 512. And let's add them. 7 plus 1 divided by 4 plus 5 divided by 64 plus 4 divided by 512. And according to this calculator, that's equal to 7.3359375. Probably approximation tool.
Will we have numbers that work out in the test?
I don't know, they could.
Can you go up a little bit?
Right, you could think that you would give us something like that.
Oh, they could happen. Have faith.
I have none.
Well, you gotta work on that.
I'm not a Christian.
375. You can leave it as a fraction, actually. Convert, find the LCD and do it and write it that way. That'll be the exact answer. If you want to do some extra math there. Now, where this becomes fun is if I said to you, I want you to convert.
Wait, tell me, is this base 8 or base 7? Because you wrote 7.254
Base
7.
8. Oh, base 8. All these are 8.
Is there like a common method for like converting from like octal to hex or something?
Could be. Might be. Now, since Steve asked the question, I want you to convert this to binary.
Do we have to be engineering?
Well, that's the only way we know how to do it. So if you want to go from octal to binary, you go, well, I know how to go from octal to base 10. We just did that right here. See it? I can go convert first to base 10. And I know how to go from base 10 what is it? I know how to go from base 10 to binary. We just did that. There's an example. Nice example. So basically, you go to Peter Pan and says, I like ticket to go to Boston. I need to get to Boston ASAP. And Peter Pan says, sorry, we don't have any bus running to Boston right now. The next one is 4 o'clock this afternoon. It's not a busy time. They're not going to send a bus. Slow time for them. But wait a minute. We got a bus that's going to Worcester in about 25 minutes. And there's one leaving Worcester at 12:30. I can get you there to Boston probably by 1 o'clock or 1:30. That's what this method is. I don't have one that takes me from here to there. At least not now. Not yet. So maybe I can go from here to base 10. That's Springfield to Worcester. Then from this, let me go now from Worcester all the way to Boston. I know this is 142 base 10. I just finished doing it 2 minutes ago. So let me take the 142 and convert that to base 10. Divided by 2. Is that a 71? No remainder? Take the 71. Divided by 2. That's a 35 plus a remainder of 1. Take the 35 divided by 2. 17, remainder of 1. Take the 17 and divide it by 2. 8, remainder of 1. Take the 8 and divide it by 2. 4, remainder is 0. 4 divided by 2. 2, remainder of 0. 2 divided by 2. 1, remainder of 0. And finally, 1 divided by 2. 0, remainder of 1. Once you hit that 0 there, you're done. Read them bottom up. 1, 0, 0, 0. 1, 1, 1, 0. Some of you might have a calculator that has, I don't know, I'm looking at mine to see, hexadecimal. It says hex on it, H-E-X-A. I don't have it on this calculator, but I'm sure other calculators have them. And what is that? That's one of the other modes that we use. The reason a lot of people sometimes want to make a code like this, you can use any base. You can make your own base 13. Because they want to make sure if you have a machine that works on base 13 and you're working for the government, now you take that information decide to steal it from the government, bring them to your laptop, and plug that in. Now it's not going to work. It's going to be gibberish. Because you use a different base. And that's how I try to protect some of the stuff actually by making a different base that people don't use. I mean, we have a lot of smart people that can have a computer at home, build their own that will work on base 2, that's base 3, that's base 4, base 5, base 6, base 7, base 8, base 9, 20, 21, make their own stuff just to make sure in case somebody does something crazy. But if you make base 20, you say, okay, or let's go with 16. Hexadecimal. That's base 16. That's a well-known one. Everyone knows that. But if I'm making a new one, because I don't want people to know anything about like base 23, we'll call it Z base 23. Well, since that's base 16, the smallest digit is what? 0. And you're going to go to where? 15. But there's a problem with the 15 because that's 2 digits. You can't use 2 digits. So we use 0 for 0. 1 for 1, 2 for 2, 3 for 3, 4 for 4, 5 for the digit 5. We'll use 6 for the digit 6, 7 for 7, 8 for 8, and here's the problem. When you hit 10, what are we going to use? They use A for 10. They use B for 11. We use C for 12. D for 13. E for 14. And F for 15. So that's what we use. So if you decide to make base 21, and if you're smart, you don't want to use A for 10 and B 11, C is 12, because that's the common choice. Maybe you decide to go crazy with that. Go, you know what? I'm going to use Z for 10. I'm going to use A for 11. I'm going to use X for, just make your own stuff. Let them at least work for it if they're going to steal your code. So now when you write a number, you go A to B, base 16, and I want to know that as base 10. What is that number? Again, the weight of this digit, that's 16 to the 0, which is 1. 16 to the 1, 16. 16 squared, which is what, 256? So that number is equal to A is what? A is 10? 10 times 256. Plus 2 times what? 16. Plus B, which is 11 times 1. 2,560 plus 32 plus 11. 1 and 2 is 3. 1, 3 is 4 and 6, 10. 0. 2603. That's a comma, not a decimal. So 2603. And if you have a decimal, you do the same thing with a decimal. I think you got the idea. How do you go from this to binary? Well, you go from this to 10 to binary. So if I want to convert this I'm going to do this to base 10 again. Which is, what was it? 2603. Then from there I need to convert that to a binary. And you can take your time and divide that in and that's the answer. 10100010111. We said, wow, that was quick. Stephen asked me earlier, is there a way to go from base 16 to base 2 quicker? And the answer is yes. And that's what I just used here. So what is that base? So before we get to that, let's talk a little bit about your book here. They talk about different bases. Notice from 16, I had 16. Let me go back to this one. 16 to base 2. Let's look at it. Let's start with the B. B is what? What number is that? 11? Let me look at 11 here. The chart says 11 in binary is what? 1, 0, 1, 1. Can you see it here on my screen? I can't enlarge it because I got to stop the video. But it's 1, 0, 1, 1. That's where 11 is. Why? Well, even if you don't see it, let me give you... Yep, let me give you the reason behind it. I hope it's not my blood number. .2. Remember I said earlier we call that what? 8, 4, 2, 1. Remember that code 8, 4, 2, 1? Well, let's think of 11. 11 is what? That's 8 plus 3. Well, how do you get 3? 1 and 2 is 3. That's why the 11 is 1, 1, 0, 1. 1, 0, 1, 1. 1 plus 2 plus 8, that's where the 11 came in. Can you see that? The 2 is straightforward. Well, the 2, look at this. If you want a 2 out of 1, 2, 4, 8, you need to have what? 0, 0, 1, 0. That's where the 2 is. That's the B, right? The B here. And that's my next group. 0, 1, 0, 0. Can you see that? That's the A. I went too far on that line there. So this is the A. This is the 2. And the next one is what? Oh, the B, the first one. First one is B. And what's this one? 0, 1, 0, 1. Isn't that 10? Well, how do you get 10 out of 8, 4, 2, and 1? You need a 1 here to give me the 8, and you need a 1 of the 2. So that's how I came up with that number.
So you used the 8 for
2, 1, because that's the binary.
you did 1, 1, 0, 1. Oh, and you like added like because like
Here's this one. I want to convert this to binary. Let me 8, 4, 2, 1. Think about the 5. The only way to get a 5 if you have what? 1 and 4. Isn't that what a 5 is?
0, 1, 0, 1.
So that'll be, let's write them from right to the left. 1, 0, 1, 0, right? So the only way to get a 5, it's actually 8, 4, and 1 is a 5. So that's we have a 1 here and a 1 here, and you have 0, 0 there. The next one is what? C. What's C equal to? Let me get my chart in case you forgot. C is 12. How do you get 12 out of 8, 4, 2?
0, 0, 1, 1.
8 and 4 is 12, right? So 0, 0, 1, 1. Next group is what? The 3. How do you get 3? 1 and 2 is 3. 7. 1 plus 2 plus 4, isn't that 7? B. B is what? 11. What's 11?
1, 1, 0, 1.
1, 1, 0, 1.
From right to left.
Yep. I'm right from right to left, yep. And the last one is what? A.
0, 1, 0, 1.
And that's that answer. I don't have to divide them. I don't have to convert to base 10. We can apply the same logic for the octal. For octal, here's the difference. For octal, we're only going to use 3 because they go as high as 7. So we use 3 digits. That means what? The weight of them is going to be what? 1, 2, 4. You can get all your combinations in 3 digits. 1, 2, 4. Let's take a 5. How do you get a 5?
101.
So that's 101. Yep. 1 and 1 here and 0 there. The 2. 0, 1, 0. The 3. 1, 1, 0. The 4.
0, 0.
And the 7. 1, 1, 1.
Way easier than going through base 10.
Yep. Okay. And you can go from binary to this and this to that backward quickly the same way. If I give you having fun with all these colors now. If I give you one like this, I want to go to base 16. Work it backward. What do I mean work it backward? Break it down to groups of 4s. There's the 14. Let's look at this. What's that? 8, 4, and 1. What's 8, 4, and 1? 13. What is 13? Is that D? The next group, 1, 1, 1, 0. 1, 2, and 4.
7.
7. The next one, 1, 1, 0, 1. 1, 2, and 8. That's 11. What's 11?
A.
Try again.
B.
B.
It's like a rather cool cheat sheet on the side with all 1, 1, 2, 2, 3, 3.
Now, how about this? 1, 0, 1, 1, 1, 1, 1, 0, 1, 0, 0, 1, point. 1, 1, 0, 0, 1. Base 2. I want you to give me that in octal. Here's my decimal point. I'll deal with that later. Let's look to the left of that first, then we'll come back to the right. 1, 0, 0. Now, octal is how many digits? Bless you. 3. So the first one, 1, 0, 0.
1.
That's a 1. 1, 0, 1. That's 1 and 4.
5.
1, 2, and 4. 7. And the last one, 1,
5.
0, 4. 1 and 4, that's 5. That's to the left of the decimal point. What is to the right of the decimal point? Groups of 3s. 1, 1, 0. That's one group.
How do you go backwards? Or
0, 1, 1. Let's think about 0, 1, 1. 1, 2, 4. 1, 2, 4. It's always the same direction. 1, 2, 4.
Oh, 6.
That's a 6.
But now we have that little 2.
I got 0, 1. Oh, I don't have another digit there. I'm in trouble. There's another 0. We just don't put it there.
Oh.
Just like in math, when the last digit is 5, that means you can put as many zeros as you want to. What is 0, 1, 0? Now I might decide to be really mean on the test. Go, you know what? You guys, this is too easy for you. That's base 16, obviously. I want you to give me the answer in base 8. Separate problems. Let's look at the A. Let's convert that to binary first. A is what, 10? That's 8 and 4, right? Now remember, in octal we have 1, 2, 4, 8. That's A is 10, so that's 1 and 1 here. So 1, 0, 1, 0. F is what? 15. To get 15, 8 and 4 is 12, 14, 15. Every one of them has to be a 1. Next one is the 3. The 3 is what?
0, 0, 1.
0, 0. I'm going left to right. 0, 0, 1, 1. Yep. And there's a decimal point. E is 14.
1, 1, 1, 0.
1, 1, 1, 0. Next one is 4.
0, 1, 0,
0, 1, 0, 0. And the last one is what? C, which is, what's C?
D.
12, right? 12, is that 8 and 4? It's 12? So we just took this from 16, made it binary. Now let's go from this to base 2. Groups of 3. In binary, remember, that's 4, 2, 1, the base. So what do we have here? Is that a 3? What's the next one? 0, 1, 1.
5.
Try again. 1, 2, 4.
No, 6.
6. Try the next one. 1, 1, 0. 3. Try the next one. 1, 0, 1.
Yeah,
5. There's the decimal point. 1, 1, 1. 7. 0, 0, 1. 1. Right? 1, 2, 4. 0, 0, 1. 1.
1 again.
And 1, 0, 0, 4. So your answer is 5, 3, 6, 3.7114. And that's how we switch from one base to another. Nothing really fancy,
It's a lot of work.
you know. Well, if, again, you want to design your own base, you can. Nobody's going to stop you. There's a lot of bases on the market. There is XS3. There is, somebody came up 1353 base. There's multiple bases because the whole idea, you want to design a machine that's unique. Why? Again, it could be national security. You want to make sure nobody else gets a hold of that machine or the information. So the only way to protect for that is by doing what we've been doing.
I don't know, but once they figure out that it's in that base, it's just like,
Well, once you figure the base, the code is broke. Yep, that's the key, is figuring what that base is. So you got to make it as the most challenging one you can think of it.
But the base can have whatever character.
Or you write.
Yep, you can use any characters for the base. Doesn't have to be, that's what I'm saying. You don't want to use A, B, C, D, because that's the common choice. So you might use X and Z and M and A and B and T for different values, and
alpha and
you know,
Different alphabets.
yep. And you might maybe want to use 1, 3, 5 and different things with them to make sure nobody gets to that machine.
So the base is like, what, like 10 digits long.
Just to give you an idea, This is the 8421 code. Remember we were talking about it? 1248? Let me stop here, the video, so I can zoom in.